Hello there, students. Today we're going to learn some simple mathematical operations that we can do to vectors, namely scaling and addition. Kind of like numbers or scalars that we are used to working with, we can multiply a scalar by another scalar, for example 5 times 5, and we can add scalars to each other like 5 plus 5. These are the mathematical operations we call scalar addition and scalar multiplication. There are mathematical operations we can do on vectors as well, including vector addition, where we add one vector with another, and scalar multiplication on a vector, which we'll learn about in this video. In the previous videos, we've been using the angle bracket notation for vectors, but inside we always had real numbers for the x, y, or z components. To be completely general, we will start writing vectors like this, with the letter of the vector and a subscript for which component we're representing. Here, a subscript x is the x component of vector A, and it is in the first position in the angle bracket notation. Then, we also have a placeholder value, a subscript y, for the y component in the last position of the angle brackets. If we consider a number line and look at the number 5, if we wanted to find out what 5 plus 5 was, we could look at this distance from 0 to 5, and then add that same distance again to find the answer. This is also the same as saying 5 times 2, or take 5 2 times. Now, if we convert these to vectors, we see that these distances on a number line can easily be seen as vectors, a vector with the only non-zero component being in the x direction. What these vectors on the number line actually represent is scalar multiplication on a vector. If our vector was 5 units long to begin with, and we know that 5 times 2 is 10, our new vector 2 times vector A should be 10 units long. We distribute the scalar number 2 into each component of vector A, getting 2 times 5 and 2 times 0, which is just 0. Then we see that 2 times vector A is indeed 10 units long, just like we expected. We can move away from our number line now and look at a vector in general two-dimensional space. A general vector might look like this, some magnitude and pointing in some direction. If we multiply this vector by 2, we expect it to be twice as long, but still pointing in the same direction, just like before, and it would look like this. We can also multiply by negative values. For a simple example, let's consider negative 1, which would look like this. We see that multiplying by a negative number just flips the direction of the arrow. We can do more than just simply multiply a vector by a scalar though, we can add vectors to each other. If we remember from the start of the video, where we had an example of scalar addition, 5 plus 5, which is the same as 5 times 2, we can go backwards to figure out how vector addition might work. If 2 times 5 is 5 plus 5, then we might deduce that 2 times a vector A is vector A plus vector A, and it is. So here we have 2 times vector A, which is equal to vector A plus vector A. But if we look at it purely as multiplying, we can distribute the value of 2 to each component of vector A to get a new vector, where each of the components is now scaled by a factor of 2. Now that we know what the final result should be, let's look at this by actually adding the two vectors together. Here we start with the same equation, but this time write out the vectors, and then add them component by component. By this, I mean we can only add x components with other x components, and the same for y components. Simplifying, we find we arrive at the same result from above. This is all fine, but what if we wanted to add two different vectors to each other? What would that look like? Let's consider two general vectors, vector A and vector B in 2 dimensions, which might look like this. To add these two vectors, we follow the process as before, where we add each of the x components together, and then the y components together to form a new vector which we will call vector C. Here we can notice that the x component of the new vector C is just the sum of x components from vectors A and B, and similar for the y component of C. Just as there was a geometric view of multiplying a vector by a scalar that we saw with the number line, there is also a geometric view of vector addition. If we put two vectors in space, let's use vector A and B again, and connect vector B's tail to the head of vector A, notice that we can extract the x and y components of vector A and the x and y components of vector B, which are these dotted lines. Then we could draw a new vector from the tail of vector A to the head of vector B. This new vector is what we have previously written as vector C. This method is sometimes called the triangle method of visualizing vector addition. If we combine the two x components from vectors A and B, and the y components from vectors A and B, we see that the sum of the respective components are exactly the new components for this vector C. This reinforces the equation above, that ax plus bx is equal to cx, and ay plus by is equal to cy. There is another method called the Parallelogram Method which builds on this triangle. The Parallelogram Method is useful later when we introduce the operations of multiplying vectors with one another. If we connect the tail of vector B to the tail of vector A, and then we place the tail of vector A onto the head of this new vector B, we can complete a parallelogram. Let's take a quick break to try out an example with everything we've learned so far. If we're given three different vectors, vectors v1, v2, and v3, what is this new vector w if it is equal to 2 times of v1 plus v2 minus 3 times of v3? Take a moment to pause the video and give it a try. Alright, welcome back. The first step is to write out all of the vectors in their component forms. Then we distribute the scalar multiplications into each of the vector components, resolve the scalar multiplications, then add each x component together, and the same for the y and z components, to finally arrive at our answer for vector w. Thanks for watching and learning about vectors. If you found this useful or want to see a specific topic covered, post a comment below or head over to my Facebook page in the video description.